If you climbed to the top of a mountain and stayed there your entire life, when you came back down, you would have aged slightly more than everyone who stayed at the bottom. That sounds like something out of science fiction. It isn't. It's one of the strangest, most well-proven facts about reality, and almost nobody knows why it actually happens. So let's start with the obvious question. How can time move at different speeds depending on where you're standing? The answer starts with gravity, but not in the way you'd expect. You've probably heard that gravity pulls objects toward each other. What you probably haven't heard is that gravity also affects something much stranger: the flow of time itself. The closer you are to a massive object, like Earth, the stronger gravity's pull is. And the stronger gravity's pull is, the slower time moves. At the bottom of a mountain, you're closer to the Earth's mass. Gravity is slightly stronger there. At the top, you're farther away, even if it's only by a few thousand feet, and gravity is very slightly weaker. That tiny difference is enough to measurably slow down time near the ground compared to higher up. This isn't a rounding error or a quirk of measurement. This is a real physical effect called gravitational time dilation, and it comes directly out of Einstein's theory of general relativity. Here's where it gets stranger. You might think this effect is too small to matter, and in terms of your daily life, you're right, it is. The difference between the bottom and top of a mountain is a matter of nanoseconds per year. You will never consciously notice it. But here's the part that should stop you in your tracks. We've actually measured it, directly. Scientists have used ultra-precise atomic clocks, clocks accurate enough to lose less than 1 second every 100 million years, and placed them at different elevations. One clock at the bottom, one clock slightly higher up, sometimes by less than a meter, and the results matched Einstein's prediction exactly. The higher clock ran faster, the lower clock ran slower. Not because the clocks were broken, because time itself was moving at different rates in those two locations. Let that sink in. We're not talking about a difference between Earth and outer space. We're talking about a measurable time difference between two clocks in the same room, just placed at different heights. So why does gravity do this to time at all? This is where most explanations start throwing around complicated physics. But here's the simplest way to understand it. Think of time and space as being woven together into a single fabric. Physicists actually call it space-time. Massive objects like planets don't just pull on things around them, they actually bend that fabric. The closer you are to a massive object, the more that fabric is curved. And when space-time is more curved, time itself moves more slowly through it. It's not that gravity reaches out and grabs time to slow it down. It's that gravity reshapes the very structure that time moves through. And near a large mass like Earth, that structure gets stretched in a way that makes time crawl, just slightly, compared to farther away. And this isn't just a mountain thing. This is happening everywhere, all the time, at every different altitude on Earth. Which means somewhere right now, there's a very real, very measurable difference in how fast time is passing between the person standing in a valley and the person standing on a hill above them. Neither of them will ever feel it, but it's real, it's constant, and it's been happening since the planet formed. Here's the detail that makes this even harder to wrap your head around. This effect isn't unique to Earth. The stronger the gravity of any object in the universe, the slower time moves near it, near a black hole. Where gravity becomes almost unimaginably strong, time can slow down so dramatically that someone falling toward it would appear from the outside to freeze in place. Frozen not because they stopped, but because time near that object had nearly stopped entirely. Which means the mountain example isn't some tiny, irrelevant footnote. It's a small, measurable preview of one of the most extreme phenomena in the entire universe, happening quietly, in miniature, every single day, right here on Earth. So the next time you're hiking, or flying, or even just walking up a flight of stairs, remember this. You're not just changing your elevation, you're changing your relationship with time itself. It's a small, invisible shift, but it's real, it's measured, and it's happening constantly, whether you notice it or not. If you want more videos on the strange hidden physics happening around you every day, subscribe. There's a lot more like this coming.